Now we're going to talk about the more complicated situation of non-uniform circular motion, which I've drawn one example of here, but as with non-uniform translational motion, there are lots of different examples of non-uniform circular motion. This one is for an object moving around a circle and speeding up. I'm going to leverage what I know about angular acceleration and angular velocity and try to make a strong analogy to what we have done with translational motion already to try to understand how non-uniform circular motion is going to work. In general, what I'll usually start with is that I might know the angular acceleration alpha as a function of time, which I could then integrate using an expression like this one to get omega as a function of time is going to be equal to some initial omega plus the integral from t initial to t of alpha of t dt. Again, this is exactly what we did when we were working with non-uniform translational motion. If we want to take another step up to get the angular position as a function of time, we can do the exact same thing, do theta I plus the integral from ti to tf of omega of t dt, where you can just take this omega of t and plug it right in there. Now, of course, these expressions look complicated because I didn't tell you what the angular acceleration was. I just supposed that we might know what it is. In general, this could be anything, right? We could have an angular acceleration that goes like t, or t squared, or the sine of t. Any of those would be possible functional forms for our angular acceleration that we could then plug in and do powerful things with. We, of course, are going to often talk about the most common and most straightforward of these, which is the case where the angular acceleration is equal to some constant, which I might decide to call alpha naught. At that point, these integrals become very easy and, again, identical to integrals that you saw for translational motion, which means we're going to get an omega of t, which is equal to omega initial plus alpha naught t, and an equation for theta, which is going to look like theta initial plus omega initial t plus 1/2 alpha naught t squared. And again, these look very familiar as the equations for constant acceleration motion that you saw for translational motion, except now we've got omegas, thetas, and alphas in all the places that before we had a's, v's, and r's.